So far last time we were learning about the alteration method. Then we saw one example of how one can use this alteration method. We show a lower bound on the Ramsey number. So the basic idea is that instead of just taking a random object and then expect the random object to be the desired object that we want, what we do is that we take a random object and then show that this is almost what we want, and we make some small adjustment to make the final object exactly what we want. In the previous example, the structure that we want to avoid was the monochromatic clique. So we delete some vertices to destroy those bad structure. And it's called alteration method because sometimes we not only just delete, sometimes we want to make some adjustment. So let's consider one more example, which requires the addition of some things instead of deletion. Let's say a set in a graph is a dominating set. If every vertex outside this vertex set S has a neighbor in S. Note that the vertex in S itself does not have to have a neighbor in S. So for example, if you take this S, then all the vertices outside has a neighbor inside of S, so it is a dominating set. Also, if you take this S, then it is trivially a dominating set. And sometimes you say a set is total dominating set. If we delete this and then every vertex in VG must have a neighbor in S. In that case, this is not a total dominating set because this vertex does not have any neighbor inside of S. But if we have these two edges, then this is total dominating set because every vertex here has another neighbor inside of S. Anyway, so this is the definition of dominating set. And one question is that when a graph is given, then how large how small can a dominating set be? So it's good for us if we find a small dominating set, because big dominating set is always we can find. We just take a entire vertex set, and that's trivially a dominating set. Also, we want to make the relationship, find the relationship between the density of G and then dominating set size S, because if there are more edges in G, then it's easier. Then what happens is that each vertex is likely to dominate more vertices, so size of S tends to get smaller. So, and how do we measure this, density? There are several ways, but one typical way is considering minimum degree. So if you have an n vertex graph with minimum degree K has always a dominating set of size and most some number this. So if you simply think about it, so we just have this one condition, minimum degree K. And it's more difficult if we have a less number of edges. So it's more difficult to find a small dominating set if we have a less number of edges. So assume the graph is K regular. Then if you have a set S, then every vertex here can have a neighbor outside and most K other one, and then they might coincide a bit more. K other one. So this. So this suggests that the ratio between S and then V of G outside of S, the ratio is no bigger than 1 to K. So this set has to be at most the K times S. So which yields that the S must be, at least N over K plus 1. Otherwise, it cannot be a dominating set. But what it suggests is that a little above that, if we add a log n factor here more, then we can always guarantee to find the dominating set of size and most this. And this is the absolute lower bound. There is no dominating. If we assume G is regular, then every dominating set must have size at least this. So, and this log factor is, kind of small compared to this K plus 1. So this suggests, give you some idea why, this bound is not too bad. So how do we want to do? Again, we want to do the alteration method. So we want to find some random object, and then we want to modify it to get a better object. So how do we do it? We want to take some random set S. So we form a random vertex set S by including each vertex independently at random with probability P. Say this P is log K plus 1 over K plus 1. Then now we have S, and then some of the vertices are dominated by S, as it has a neighbor in here. Some of the vertices outside of S. But some of the vertices might not be dominating by S. Then S itself may not be a dominating set, but we want the set to be dominated. So what we do is we take this as T, and then our plan is to take this as our dominating set. So every vertex here either has to be included in S or has a neighbor inside of S in order for S to be a dominating set. So these vertices doesn't have any neighbors inside of S, so that's problematic. So what we do is we just add them. Then this is surely a dominating set. So given S, let T be the set of vertices outside S having no neighbor in S. Then S union T is a dominating set. Keep in mind that this S is a random variable and T is also a random variable. T is a set which is obtained in random. Then this is our object, so we want to make sure that this is not too large, so we want to consider the expected size of this. So what do we know? Expected size of S is just NP, because each vertex appears in S with probability P. And what's the expected size of T? For that, when we have a vertex, then when does it become a member of T? If all of its neighbor, B, and then say this is x1, x2, xd, all of them are not in S, and not in S, and then B itself is not in S. Then this B belongs to T. Again, let's say that the xb is the indicator random variable. Which is 0 if B is not in T, and which is 1 if B is in T. Then, what's the probability of this event? xb is 1 only when all of these are not in P, which are all independent events. This happens with the probability 1 minus P. So there are 1 minus P, degree of V, many plus 1. And what do we know? We know this degree of V is at least K. So this is at most 1 minus P to the K plus 1. So we have this upper bound. And then we can actually ensure that we know this inequality. So this is at most e to the negative P times K plus 1. So this is more convenient expression for us, so we use this. Because the difference between these two are not so big, but this is more convenient for us. So what do we get? We know that this expected size of S plus T is at most MP plus N times e to the negative P times K plus 1. But what was P? P was log N over, log K plus 1 over K plus 1. So this becomes negative log K plus 1. E to the negative log K plus 1 is just the K plus 1 over, 1 over K plus 1. And then P is, as I mentioned before, so this has log K plus 1 over K plus 1 N. So this suggests that there exists a choice of S such that which yields the size of S together with T is at most this number. So this completes the proof. So like this, we can actually, add the vertices. So modification could be deletion or addition. And, we take the expectation of the final object. And then implies that there is a choice of S. And we don't care how large S is, but together with T, it's at most this much. So that's one example. And let's consider one more example. Not one more, maybe more than one, but another example, let's say. So as before, we can again consider the two coloring of hypergraphs. So before we have proved that, this MK, which is the smallest number of, edges in a K uniform hypergraph, which is not two colorable. And we have proved that, this MK is between 2 to the K minus 1 and K squared times 2 to the K minus 1. Of course, times some constant. And later, back in 1978, prove a lower bound of K to the 1/3 times 2 to the K. So this is just the exponential, and here you multiply by some polynomial, and later 레다리시넌 and Srinivasan 2000 further improve this to 2 to the k times k over log k to half. So roughly, I mean, log is smaller than k, so this is roughly k to the 1 half, and this is roughly k to the 2. So there are still some gap. And now we want to show the lower bound, this lower bound. So let's prove this. If there is p, which is by s times 1 minus p k plus s squared p is smaller than 1, then mk is bigger than s times 2 to the k minus 1. So, I mean, this expression is that later we will make sure that the number of edges, okay, let's recall how we have proved this. We choose some n vertices, and for, and we give me a moment. No. So, how did we prove the lower bound? Lower bound is that we want to show that every k-uniform hypergraph with this many edges can be colored with 2 colors. And how did we show it? Assume we have a k-uniform hypergraph with this many edges. And then, for each vertex, we either color it with red or blue. And then, prove that if there are this many edges, or smaller than this many edges, so actually minus 1 many edges, then with positive probability, we can show that every edges are not monochromatic. So that provides a lower bound. So here, what we want to do is we want to color the vertices by blue or red. Let's say we have this many edges, and we want to color the edges with the blue or red. For now, we want to color, before it was blue with probability half and red with probability half. But now what we want to do is slightly differently. We want to color this with blue with half, 1 plus p over 2, and then red with 1 minus p over 2. Then we have a slightly more edge than before, but this red probability is also smaller. So even with this condition, we can show that there is no red monochromatic edges. But now blue is even bigger, and there are more edges. So we have quite many blue monochromatic edges. But we will, by hand, we will correct some, color of some vertices to kill all blue monochromatic edges. And then, in order to choose this P, what we will do is we will choose P which satisfies this condition, where S is, this is the number of edges. So that's our plan. With that, we first show that this holds, and then later we show that we can actually choose S and P wisely, so that these conditions satisfy, and then we get this answer. And one of the technique that makes our proof more convenient for us is that we, instead of discrete, analysis, we consider the following continuous framework. So sometimes this is a technique which makes some analysis easier. What we do is, for each vertex in V, let xb be a real number in the 0-1 interval, which is chosen uniformly at random. We call this xb the label of V. So for each vertex we have these labels. And one thing we notice is that since there are finitely many vertices, for all V xb, for all the vertices, xb are all distinct with probability 1. So we just forget the case where there are two vertices with the same label. Assume that doesn't happen. Because even if that happens, later in our analysis of our computation, those events will happen with probability 0. So later we will show something happens with a positive probability. And from there, even if you subtract or add the probability of the event, which is 0, then the answer doesn't change. We only care whether some event at the end is positive or not. So why do we give this label is that we want to obtain this ordering. So according to the value of this, we get an ordering. So several vertices, if this has 0.1, VWU, 0.2, 0.15, then we get the ordering V, U, W, and so on. 0.1, 0.15, 0.2. You can imagine this as from 0 to 1, you are moving along this line, and then each time, while you are moving, you kind of select one vertices from here and then put, and then you are moving again at some random point. You, choose again a vertex at random, and so on. But okay, so this is another interpretation, but it might be confusing you. So let's just forget what I just said here. So this actually gives you an ordering. We might as well take arbitrary permutation of the vertices and then do the computation over there, but it's more messy. If you do the computation there, it's more messy, but here it's rather simpler. So we take this, model. So now for each hyperedge E, we say that a vertex in E is the, say, first or last vertex of E if xb is smallest or largest among all xu with u in E. So we have this hyperedge UVWX And then this has value 0.1, 0.3, 0.2, 0.15. Then this is the first vertex and this is the last vertex. Because if you enumerate that, then U, X, W, V, you get this, vertices in this order. So this is first vertex and last vertex. And now what we do, we take a 0, 1 interval and we divide into 3. L, M, R. L is between 0 and 1 minus P over 2. M is between 1 minus P over 2 and 1 plus P over 2. And R is the interval between the 1 plus P over 2 and 1. These are 3 subintervals. So now we will color the vertices depending on the value of this. So if XB is in L or M, then we color B by blue. So as our plan, we want to color the vertices with a probability so that the blue is a bit more likely than red. And if it's in the right interval, then we color B by red. So as this now, the probability that the random H becomes monochromatic is 1 minus P over 2 to the K. But here it's implicit, but later the number of edges is slightly bigger than 2 to the K, which is much smaller, which will be much smaller than 1 minus P over 2 to the K. So even if you take this and multiply with this number, it will be small. So, we will be able to avoid any red monochromatic edges, but there will be much more blue monochromatic edges. So, now we recolor some vertices to avoid, to destroy all blue edges. How do we do it? We do as follows. For any vertex V whose label is in the middle interval, if V is the last vertex of a blue monochromatic edge, then we recolor B to red. So this is what we do. So after doing that, what happened? Now there are no, there could be 2 types of monochromatic edges. Either blue, if there are still blue monochromatic edges, then this must contain no vertices which lies here. So the labels of these vertices inside of this edge will be completely in L. And also there could be a red one, monochromatic one, which used to be, not monochromatic, but now it becomes red monochromatic because some of the vertices in M was previously blue but now red, and then it becomes the new monochromatic red edge. But we want to compute the expectation of this, and there are also original red monochromatic edges, which is not likely to, it is likely that we can avoid this. So we have to consider these 3 types of monochromatic edges and then show that we can actually avoid them. So let's consider these 2 types together. So there could be a monochromatic edges which either lies entirely in L or entirely in R. So there could be a monochromatic edges lying entirely in L or R. So what's the expected number of such edges? Is that we just have this. So for each edge, it's either entirely lying in L with this probability or entirely lying in R with this probability. So the probability that one of them happens is 2 times this. And there are, number of edges in H many edges. So from here, what do we know? At first I think I didn't say anything about H. Let's say H is a hypergraph with this many edges. K uniform hypergraph with this many edges. Then you just multiply it here, then what you get is this inequality. And second type, HE, which becomes red monochromatic only after recoloring, which was not monochromatic, but it is. Then what's the first vertex of E? So on this interval, we have again M, L, R. On this E, there must be the first vertex which lies inside of M. There could be more than one vertex lying inside of M, but we have a first vertex, V. The first vertex. So for such E, the first vertex B of E must be blue before recoloring, but becomes red after recoloring. So this becomes red after recoloring means that there is a blue monochromatic. Before recoloring, there was a blue monochromatic edge which contains V as its last one. But in E, V is the first one. So in F, V is the last one. So they must intersect at one point only. Hence, such an HE actually belongs to a pair, say FE of edges of H. Where E intersection F is a single vertex B. And this XV is in M. And V is the last vertex of F and the first vertex of E. So, if we have two edges, F and E, and V, which shares one common vertex only, for a pair FE with whose intersection size is 1, what's the probability let's write this. The intersection is just one vertex P. The probability that this happens here, this means the E was was not a red monochromatic before, but F is a blue monochromatic, and then you change this, color of B, and then now E becomes the red monochromatic. So this can happen with the probability is so. The probability, let's write it this way. For fixed xb in M, the probability that this happens is that this. So what it means is that once you fix this xp, then all the vertices in here, in F, must lie within this range. That happens with the probability x sub b to the k minus 1. And all the vertices here must lie in here, which happens with the probability 1 minus xb to the k minus 1. And we know that they sum to 1, so we know that this is at most, 1/4 to the k minus 1. So also we in order to that, for the this happens. For this to happen, for this pair, we also, in addition, have to have this event that xp happen to be in M. So this says that for, say, such a pair, Fe, the probability of this happens and most P times 1/4 times k minus 1. So you first choose xp, and then that happens to be inside of M, which happens with the probability P. If that happens, then for the remaining vertices, all of them are, all of these are before x and all of these are after x happens with this probability. So this happens at most with that. But how many such pairs are there? The number of such pairs are s squared times 4 to the k minus 1 such pairs Fe because you choose one edge, then that's s times 2 to the k minus 1 and another one s times 2 to the k minus 1, and then you multiply. You don't, do you have to take the multiply too? Maybe not, but anyway, it's not so important about whether to multiply 2 or not, but there are many such pairs. So the expected number monochromatic edges of second type, say second type is this, the monochromatic edges, which becomes red monochromatic only after recoloring. Then that's, there are this many pairs, and each of the pair produces one such monochromatic edges with this probability, and that's almost S square P. So what's the expected number of monochromatic edges is at most, the first type was this S times 1 minus P to the K, and second type is at most S square P. And our assumption was that this is at most 1. So, strictly less than 1. So this happens. And this shows that the above algorithm, recoloring algorithm, produces a coloring with no monochromatic edges with positive probability. That implies that there exists two coloring which avoids all monochromatic edges. So using this, we can actually show what we wanted. So 2 to the k times k over log k to the half. All we have to check is that with the appropriate choice of S and P, we can actually ensure this happens with this number being our target number. Our target number, this. So this will be our S. So again, we use this. So then we get this. Sorry, S. So we want to minimize this. Because we want to show that we want to make sure that this is small. So to minimize right hand side, choose P as a log k over S over k. Give me a moment. K over S over K. Give me a moment. 아이고, what did I write here? Sorry, let me check some calculations. So, if you put this back here, then what do we get? So let's do one by one. S squared over k is first term, and then on the second term, you will get k over S squared log k over S. which is s squared over k, 1 plus log k over s. So this is what we will get. And we want to make sure that our goal is to make this smaller than 1, then this is automatically smaller than 1. To make this smaller than 1, and you might think that why do we choose this? In order to minimize this expression, I mean, you can consider this as a function of p, and then you take the derivative and then let it to be 0, and then you solve it. Then you can, I mean, choose the appropriate p. Anyway, in order to make this smaller than 1, we can also figure out that this is a good choice, assuming k is large. Then it's easy to actually check that you just plug that in. Then this expression is smaller than 1, and the previous theorem applies. And with this choice of s, now you conclude this. So this is one application of alteration method, and then in the next video we will learn more about the alteration method.